Hey, this is Brock Lemires, and in this video, I'm going to introduce the concept of pointers in the C programming language. All right, so when we declare a variable, okay, this is what we've done up until now. You give it a name, and we've been calling it a name, but we can also call it a reference or a label, and we can assign it a value when we initialize it, and then you give it a data type. Okay, and what that means is that you are going to put information into memory at some space, and it will, depending on the data type, it will dictate how much space it is. In this situation, an int, it'll reserve 4 bytes or 32 bits, and it'll also define how you encode the information. So 109 is going to be encoded as a 32-bit signed integer number, okay? What's cool about this is that the operating system itself takes care of where in memory this goes. So you don't have to keep track of the absolute address. And that becomes, because if your program gets larger and larger, it becomes a little tedious to try to track these things, okay? However, there are times when we do want to track the exact address of where information is, and that is done through the concept of a pointer in C. A pointer is actually a special variable type that will hold an address. So for example, 109 is sitting at this address. Let's just say it's at 7F00. We could potentially set up a pointer as another variable that would hold 7F00. And by doing that, we can actually access this information in this location using its address. Now you'll see why that's important as we go, and it just takes time. The more you program in C, the more opportunities there are where you're like, man, I really wish I had the starting address or the address of this. It becomes especially important when you work with arrays because you want to actually go to the start of an array and then cycle through every value. Okay, there are special syntax dedicated to pointers in C, and let's go through a couple of them. So the first one is this ampersand. This is called the address of operator. And what you do is if I put that in front of a pre-existing label, it will return the actual address. So if I look at how that would look when I coded it, I would do ampersand n, and then I could assign that to a variable, all right? The next special syntax is the asterisk, and that's called the value of operator. And it can be used two different ways. The first way is when declaring a pointer variable. And that's how it's used in this example right here. So let's look at this. I'm going to create a pointer variable called P, and I denote that it is a pointer variable by giving it an asterisk. So that's different than if I just had a variable name alone. This tells the compiler, hey, this variable is only going to hold addresses. Okay, it's only going to hold addresses. And then I can assign to it the address of another label. So if I did this operation right here, what's going to go in there is the address of where the label n is. So for example, if I ran these two, I would actually put in this location 7F00, which is the address of where 109 is stored. Now there's a data type with this. The pointer always holds an address. Okay, but you do assign a data type to it that indicates what is held at the address that this is pointing to. So you're not giving it a data type for what's in the pointer location because that's just bits, that's just an address. You're giving it though what this location is. So it's pointing to an actual integer. Okay, so that's what that is. All right. Now, the second thing that you use with this value of is it'll return the value of an address. So I can actually do some assignments later, and if I put that on the right-hand side next to a pointer variable, I can actually read out what the address was. So I could actually read out 7F00. So this is using two different and separate models. Okay. All right. C also provides a format specifier for when you want to print a pointer, and it's %p. And %p is interesting because it just returns the address, and it actually does it automatically. It prints the address in hex. You don't have any control over it, and it prints as many bytes as the machine allocated, and it automatically puts 0x in front of it. So if I did this, let's say that I had this fictional code right here, and I said I'm going to set up p is a pointer variable, and it's going to hold the address of n, so it holds 7f00, and then I said the address of %p is p right here, that would return 07f0. I could also do the exact same thing by saying print into this format specifier %p the address of n. Okay, so the p variable, the pointer, actually is instead of doing this each time. Okay, all right, so life is good. Let's do it. Okay, so I'm over here and I'm on the Linux server, and what I want to do is I would actually want to create a new directory for this code along. So I'm going to go cd mod 09 underscore code along, and I'm going to, I'm not going to change into it. I'm going to make directory mod 09 underscore code along, and then I'll change into mod 09. I'll hit tab and it'll autocomplete. And now I'm in here. I check out what's in there. Nothing's in there. And then I'll do vim. Before I do that, my font is a tiny bit small for a video. Let me do this. Let me pop this to a 24 so it's a little bit bigger. Okay. And now what I'm going to do is I'm going to vim and I'll create something called pointers1. Okay. So vim pointers1.c. All right. So I'm in vim. Okay. And I'm going to do insert, and I'll do a comment header. So playing with pointers. And then I'll come down here and I'm going to do pound include standard IO header, because I'm going to use the printf. Okay. And then I'll set up my main function. So I'll go int main void and then open curly, come down here, return 0, and then close curly. And now I come back up here and I'm ready to begin. So the first thing I'm going to do is let's create a normal variable. So int, it's going to be called n. That's a label of it. It's reference, and it's 109. Good to go. All right, now let's do the pointer. So in this situation, I'm going to say, I'm going to create a variable that is a pointer. It points to another location that holds an integer, but this is the pointer variable. Now I'm going to initialize the pointer variable with ampersand n. So it is going to hold the address of where n was. Now you don't know where this is. It's the operating system is going to actually do it, or actually assign this address. But let's take a look at how we do this. So let's do this. I'm going to say print a line return, and you'll see why, because I'm going to print these over and over and over, and I want to be able to tell what addresses are coming back. I want to print this address that we're seeing, and so I don't want them to just be all in a row, like with no line return, so I can't tell what's what. I want to see the actual execution. And then let's do this. Let's just printf, and let's just do n equals and do it just like we've done before. So a format specifier %d, that means an integer in decimal format. I'll do a return, and I'm just going to print n. Nothing new at all. Okay. Now what I'm going to do is I'm going to go printf, and I'm going to do this. This is new now. Address of n equals, and I'm going to use the new format specifier for a pointer, which is %p. And then I'll return it. And then in that spot, I'm going to print the value p. Okay. And I'm going to go ahead and printf, and I'm going to do a line return now. And then let's see what this gives us. Okay, so this is the pointer variable. When I use it here, I don't put the asterisk or ampersand. I just say, hey, print the pointer address. Okay, so let's run this up. So I'm gonna come down here. Again, my font, I shrunk it for something else I was doing. So I come over here, boom, boom, boom. Let me change it to my mod 09 code along. Take a look, there's my pointers. Now I'm gonna do GCC, then I'm gonna do pointers1, direct the output to pointers without the C, and life is good. Take a look at what I got. All right, so I'm gonna go /pointers1, and that tells it look in the means look in the directory I'm in, not in the Linux path. Holy cow, there it is. Let's check it out. All right, so I got this. Clear that. Now I look at this, I'm like, oh, look at that address. That's a big address. And it's because this is a big server. Okay, there's a lot of address locations. There's a whole lot of bits in here. I mean, this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Holy moly. 12 nibbles. That's 12 times 4. What is that? That's like 48 bits of address. That's a lot. That's a lot. Let's run it again. Wait a minute, wait a minute. Why did it change? It's different, right? It's different. Why did this change? All I did was run it again. I didn't compile or anything. That must have been an error, right? Oh, it's different again. Oh, it's different again. What is going on? So here is the interesting part. This is what makes computers so programmable. The operating system itself gives you memory. So when you compile a program, you're just basically, it's going to run and it's going to say, hey, computer, I need some memory. I need 32 bits to store an integer, and I'm going to need apparently a lot of bits to store this pointer address. And the operating system, when you run your program, when I do this, // it says, hey, we have a request for a program to run. Here's the executable. I'm going to go ahead and give it memory, but you don't know where you're going to get the memory. Okay. The operating system does that for you. That's why it's different every single time. And that's good because basically the operating system handles like what memory is used for what, and it dynamically allocates it for us. Okay. So that's kind of cool. All right. Let's do one more just to prove that this address of n works. So if I come in here, I'm going to hit escape and I'm going to go YY to yank this line, and I'll hit P to paste it. And I'm going to do the exact same thing, but just to prove to myself that this works, I'm going to do n%n. That's the address of n. And then I'll go ahead and save that. Now I'll come down here. Let me clear this up. Let me move this down so you can see the full code. And I'll go ahead and say GCC, and then I'll do run it. And they're the exact same. So these two are identical to each other. So just the pointer variable is just a little bit easier to work with. Okay. All right. Life is good. Let's access the value though. Now we're sitting here going, okay, how do you use the thing? So watch this. I'm going to go, I'm going to come down here and I'm going to do this. I'm going to say printf, and I'm going to say using n equals, this is how we normally do it. Using n equals %d return and n. Okay, nothing new. That's absolutely nothing new. That's just how we do it. Okay, we use the label n to print right there. Now watch this. Print f, and I'm going to do, I'm going to say using the pointer variable n equals, and I'm going to print the value of n. So I still do the format specifier of %d. Okay, but this time what's unique is I'm going to put and or asterisk p, meaning value that P is pointing to, not P itself. If you want to print the address P, you do it this way. This is how you say, give me the value that this thing points to. Okay, the value of what you point to. All right, so that's good. So let's go ahead and see if this works. GCC it. Let me clear that, bring it on up. And I go boom. And look at it. It worked. It got the same information. And so we were able to do that. Now the address is changing every time, but it doesn't matter. The operating system is taking care of this for you. Okay, so that is pretty sweet. Now let's talk about terminology. This way of doing it is how we've been doing it forever, since the beginning. This is called directly referencing a value. Okay, the content of the variable is the value. All right, and it's just a direct reference. In here, we're indirectly referencing the same value, but it's indirect because we're grabbing the address first, then we go to that address, then we get the information. Okay, so that's the pointer part of this. All right, now pointers can point to any type of data type. Right, so we've done a couple examples where we did this, but just to prove it out here, let's do this and get more stick time. So let me say I'm going to have int. And I'll say a int equals 22. And what I'm going to do is I'm going to do an operation where I copy that to another variable and I'm going to do it with a pointer. Okay. So I'm going to do that with a pointer. So I'm going to come down here and I'm going to do this copy. Okay. So here's what I'm going to do. I'm going to set up a pointer. So I'm going to set up a pointer and I'm going to say this int. Okay. And then I'm going to go set up a pointer called a pointer, and please initialize it with the address of a int. Okay. And now that's good. What I'm trying to do is I want to make an assignment to bint, but I want to do that using the pointer. So let's do this. I'm going to do value of where this pointer points to. Okay. Life is good. So let's see if that works. So now what I'm going to do is go print f, and I'm going to say oh, don't yell. A int holds %d, okay? And then we'll put in there a int, so we'll directly reference it. And now what I want to do is I'm going to do the same thing, except I'm going to print what is in B. And I want to see if I actually copy this correctly. So let me YYP that. And then I go boom, boom, boom. And then I'm going to come over here. I'm going to say B. Okay, so I'm doing this. I'm doing this to see, did this copy right here work? Was I able to use the pointer A to access A int and assign it to B? And did it work? Okay, so let's go ahead and see if that worked. So I GCC it up and then let's run it. And lo and behold, it did. Let me clear that and bring it up a little bit. So I was able to do it. So what was so cool about that? You didn't just say B int gets A int, even though you could have. This isn't not how you use pointers, by the way. You use pointers when you access large arrays of information, but you got to know what they do. So that's why we're spending the time to do this. You said, I want to reference A int indirectly by using its address. So I'm going to set up a pointer variable and initialize it with the address of where this location is. I don't care where it is. I just need to know I just needed the compiler to give it to me. And then I'm going to use that address to indirectly reference the 22 that's in there and assign it to B. And I proved to myself that it can actually work. Okay. All right. So now can you do that with another type? So we've been doing this with integers. Let's try this and see what the difference here is. So I'm going to say C dub, and I'll go, we'll make it a real number, negative 1.6 O2 e to the negative 19. Okay, charge of an electron. Okay, let's clean this little fella up. And I'm going to come down here and I'm going to set up a double called D dub and not initialize it. Now you're like, okay, let's think about what we're doing here. The pointer is an address. That's all it is. It's an address. But it points to a location that holds a specific data type. So in the A int and B int examples, when I did this copy, it knew that this was going to be pointing to an integer and it was assigned to an integer. So this little fella right here. Okay. So the pointer was pointing to an integer type. You have to give it the type that it's pointing to. So now let's come down here and let's do this. Okay. So I'm going to do the following. Let me do the copy now. So I'm going to say, now what I'm going to do is I'm going to set up a pointer and I'm going to call it C pointer, and I'm going to assign it the address of C dub. Okay. So let's stop for a second and think what I did. I created a new pointer variable and I initialized it with the address of C dub, which is this location. But I had to tell it also when I set this up, hey, this is holding a double. Okay, this is holding a double. This is really important because it has to do with the offsets. So if you then came in and said, let's say that there was another variable, or let's say that C pointer was pointing to the beginning of an array, you have to know the offset in between each element. Notice that A pointer is pointing to something that's an integer. It knows by setting it up and telling it it's an integer that it's going to be 4 bytes in memory, but this one's setting up for something that's 8 bytes in memory. That becomes critical when you iterate through arrays because you need to know how far off an address is the next value is. So let's go see if this is working. I mean, it's going to work. Do D dub equals, and now I'm going to indirectly reference this value C dub, and I'm going to do it with its pointer. So I go value of C pointer, and then I'm going to do my print statements. Okay. And if you don't mind, I'm going to go YY, and I'm going to go PP right there. I'm going to hit PP, and I'm going to go C dub, and then I'm going to go D dub, and I'm going to hold these, and I can't do the %D format specifier. I've got to do, let's do E since this is such a scientific number. So I'm going to go 0.4E, and then I'll go 0.4E. And then over here, I'm going to, instead of doing this, instead of having this be A int, I'm going to make this C dub, which is holding the original value. And then I'm going to come down here and I'm going to go D dub. Okay. All right. Let's see if that worked. So I go ahead and compile it, go ahead and run it. And lo and behold, it did work. Okay. Let me clear that and run again. And it's like, okay, it worked. That's cool. Very important. It seems really simple. It's like, yeah, whatever. It's that when you do arrays, it becomes very important to know how big things are. Okay. And this works for car also. Okay. So let's do a car really quick, just to wrap this up and just to prove it to you. Cause I know you're like, I don't believe you. We'll do some copy and paste here though. Okay. So watch this. I'm going to go car and then I'm going to say, e car equals capital C, and then I'll go car and I'll go F car equals nothing. Okay, that's where I'm going to copy it to. And then down here, I'll put my copy. So I'll come here and I'll go, or I'll set up my pointer. So I'll go car, and I'm going to set up a pointer pointing to E, or excuse me, I'm sorry. E pointer is going to be initialized with the address of E car. So that is now a pointer that's pointing to this location right here. And it knows that it holds a type car, which is 8 bits. So that means if you had a bunch of cars in a row, they would be offset by each other by 8 bits. Okay, so now let's do the copy. So I'm going to copy that into F car using an indirect reference, but so I'm going to use the pointer E car. So I'm going to go E car. Okay, and it's like, oh, not car, pointer. So now I did it. And now what I want to do is I'm going to go like this. I'm going to go into visual mode, and then I'm going to go down and then I'll Y to yank it. And then I'll do that. Didn't go in the right spot at all. So let's do that again. So I go into visual mode, Y to yank it, P to paste it. I come over here and I'm like, okay, this is now holding E car. This is now holding F car. And what I want to know is now I'm going to print this as a car. So I go use the format specifier for a car, which is %C. And now what I want to do is I want to print E car and I want to print F car. And let's see if this works. Okay, so I come down here. Let me get this, let me bring this down so you can still see the code. And what I'm going to do is clear this up, GCC it, and boom. And then I'm going to run it. And lo and behold, it works. Okay, so that's it, right? That's pointers. And this is cool. Okay, now how big is the address? Okay, let's do one of these, just do a size of it. So I'm going to go printf, and I'm going to do this. I'm going to say, I want to know how many bytes this address is holding. Okay, so I'm going to go a pointer has size of, and this is going to be long double bytes, and that's what is returned when I do this variable, size of. Let me pull this over. So I had to go size of a pointer. Almost done here. Hang on. Let me make sure this is easy way. I had to change my font. There we go. Boom. Oh my goodness. Come on. Okay, there we go. So now a pointer has the size. I'm trying to find out how many bytes this uses for the address. The answer is 8 bytes. So it's holding an address. Well, what about C pointer? Is that going to be different since it's pointing to a double? So a pointer is pointing to a integer. Is that going to be different address size? It's like, no, it's still 8 bits or 8 bytes. And it's like, well, what about the one that's pointing to a car, right? Car must be different because it's pointing to something that's only 8 bits, right? These are all pointing to different data types. They must have a different size, right? The answer is absolutely not. They're all 8 bytes. Now, 8 bytes is a lot of bits. This is 64 bits, right? That's how much room it saves for a pointer address. These are all the same size because they're all pointing to an address. The address is always kind of the same thing. It's a hex value that represents the address. Now let's look at finally the addresses of all these different variables. So I have the ability now to essentially do what's the address of all my variables. So I have A int, B int, C dub, D dub, E car, F car, and you can even do the pointers, okay? And so if I come down and look at this and I print out all their addresses using the format specifier for a pointer, you look at them and you're like, okay, well, they're in descending address order, which just is how the operating system decided to put it, which is fine. But let's go look at this one specifically. Let's go down here to F car, okay? So F car is located at a bunch of hex characters and then 36. Notice that the next one in memory that holds a variable is eCar, and it's only one address away. So that means, remember, one address corresponds to 1 byte. So going from 6 to 7 is basically where fcar is. And so it's stored at 36, but the next available address is 37. Why was it only 1 byte away? That's because it's holding a car. All right, now let's think about this. The starting address of ddub is only 1 byte away from one address away from eCar, and that's because eCar is 1 byte. So it's only holding one address. Now let's look at this one. ddub is like starts here, but where's the next available address? Well, it goes to 38 to 40. So how many bytes is that? So let's go like 39, 3, it doesn't go to 40. 39, A, B, C, D, E, F, right? And it's like, and then 0. Okay, so that's 8 bytes. So the difference between 38 and 40 is 8 bytes. Why in the world would it be 8 bytes? Well, it's because it's 64 bits, because it's holding a double. Okay, it's holding a double. And then the same thing goes right here. It's like, okay, that's pretty cool. And then if you looked at it right here and you went C, B int is at this address, and you're like, well, how far is A int away? And it's like, well, it's D, E, F0, it's 4 bytes away. Why is that only 4 bytes away? That's because they're storing integers. So when you look at everything in memory, you can see that it's like, the compiler packed this in there as close as it could, but just based upon the data types, each data type only takes a certain amount of memory. And you can see that when you look at where everything is stored in memory. And so this is really cool because the compiler can keep track of like the offsets in between variables for us, so we don't have to actually manually add in like an offset of 8, offset of 4. Okay, that is it. That is pointers. Okay, so like I say, that's the overview of it. We'll use these a lot when we look at arrays, but that gives you the background to get started, and see ya.